So I am Robbie Ostrow. I am a software engineer at a company called Vanta in San Francisco, but don't blame them for what's coming. I should disclaim this talk by warning everybody to definitely not try any of these tricks at work. So I'll spend most of the time totally abusing the type system to do things that it really shouldn't do. We'll define the natural numbers from first principles so we don't have to rely on JavaScript's implementation. Next, we'll implement some operations on those numbers and use those operations to implement a checker for the Collatz conjecture using only the Typescript type system without any generated code at all. Finally, if there's time at the end, I'll use all that we've learned to motivate why the ts-json-validator project that I wrote is possible, and we'll briefly go over that and why I think it's cool, but only if we have plenty of time and interest. So first, why shouldn't we trust JavaScript? Well, as everybody knows, JavaScript numbers can't be trusted. As we were discussing earlier, if we ran fast check on JavaScript triple equals, we would see that it is not indeed correct. Honestly, JavaScript can't be trusted in general. You never know when something might break. We're doing precise mathematics here, and JavaScript numbers clearly can't be trusted. What I'm saying is, trust yourself, don't trust the ECMA committee. So I'm happy we use the strict TypeScript flag. It makes our code much safer, but it's a real bummer that TypeScript doesn't offer an extremely strict flag. And so this flag would guarantee totally side effect free code, by which I mean all of the code is stripped away at runtime and no code at all is generated, which means that nothing can go wrong at runtime, which means, of course, in turn, that you are a responsible programmer. And real programmers do all of their computation within the type system because no JavaScript code means no bugs at all. And you can skip all of property-based testing. If you have no code, you can't have any bugs. So some might complain that JavaScript is convenient and has silly things like numbers and addition built in, but honestly, that's the problem. I can't reason about numbers if I don't know exactly how they're defined. So let's define some numbers. You're used to thinking of natural numbers 0, 1, 2, 3, etc. as Arabic numerals. But the natural numbers are really just a set for which some specific axioms hold. We can name them whatever we want, but by convention, 0 is the building block of these natural numbers. Our friend Giuseppe Peano in the lower left formalized these axioms in the 19th century, but they've been pretty widely used ever since. So you don't actually need to know the Peano axioms, and I'm not going to go through them one by one. But long story short, there are a set of statements about the set defining the natural numbers that we intuitively agree upon. And they were the first real formalization of the natural numbers and continue to be used all the time, as I said. So great. Now let's dive into TypeScript. We have a simple type here, which I've called natural. So far, it's entirely useless. As you can see, it fulfills exactly 0 of the Peano axioms. We need to define 0, and it's pretty easy to see that 0 is indeed a natural number. And when I say is here, I mean extends. So in the type system, when I'm talking about the concept of is, I say A is B if A extends B. So the 0 type here extends the type natural. So we have the type natural, we have the type 0, we see that 0 is a natural number. Now, we also need an equality relation. And you can think of extends as similar to a subset relation. And if you've ever taken a set theory class, you've learned that an easy way to prove that two things are equal is that they're subsets of one another. This equals type just says, if A extends B and B extends A, then they're equal. That's basically the same thing as saying that if the subset of types assignable to A is the same as the subset of types, rather, if B is assignable to A and A is assignable to B, then B equals A. So I'm not going to prove that this equality relation is reflexive, symmetric, and transitive, but intuitively, it should make sense. If A and B are the same type, then they're equal. If they're different types, then the equality relation will resolve to false. And we're going to use conditional types pretty heavily here. So if you are not familiar with conditional types in TypeScript, the basic idea is that it's basically a ternary that takes in the initial condition and executes it against the TypeScript type checker. So finally, we need some way to transform one number into another. This successor function S suffices for the final 3 axioms. So the successor function basically just says, if I have a natural number t, or n, then S of n equals what we think of as n plus 1. But remember, we don't have any concept of plus. This is just somehow in this set of natural numbers, s of n is another number in the set that is in some sense bigger than n. So from these 4 lines of code, we have now defined the natural numbers and exactly 0 generated JavaScript. So, so I don't have to do live coding. I've just taken a little video of the TypeScript playground. And as you can see, we have this natural number type. We see that 0 is indeed a natural number as promised. And we can look through these numbers and see exactly how the TypeScript compiler ends up expressing them. They end up being pretty big recursive types. And we see also that is 1 equals to 2 is false, and is 2 equals to 2 is true. So everything so far is passing our sanity checks. And if you want to follow along, there's a blog post at ostrow.ws that has all of these TypeScript playgrounds. And I just sent that to the chat if you'd like to look at some of these playgrounds. So a quick detour here to motivate why we're doing this. So let's define a classic problem in number theory called the Collatz Conjecture. One thing I love about number theory is how easy it is to define some problems that turn out to be really incredibly hard to solve. So the Collatz Conjecture is a still unproven statement that basically says, let's take any natural number. If it's even, have it. If it's odd, multiply it by 3 and add 1. Repeat. If you do that enough times, you'll end up at 1. So a little more formally, we see this function here, f of n. We repeatedly apply f to some number, and we say eventually we'll get to 1. When it's even, n over 2. When it's odd, 3n plus 1. So to check the Collatz conjecture, as we saw on this previous slide, we need division by 2, we need multiplication by 3, repeated application of a function, addition by 1, and evenness checking. So in order to do this, instead of implementing somehow Collatz compiler, we might as well just implement addition, subtraction, multiplication, and division, and evenness checking. So let's do that. So here we'll define those 4 basic arithmetic operations. But to do that, we do have to define one helper type, p of t, which is just the opposite of s of t. So if you think of s as being like n plus 1, then p is just n minus 1. It's the inverse of s. So since we defined our natural numbers with this convenient previous pointer, which wasn't strictly necessary to fulfill the Peano axioms, this was easy to do. It's also easy to see that p of 0 is never, which makes sense when we're dealing with the natural numbers because there's no concept of negative in natural numbers. In general, we'll assign never to any type that doesn't make sense with our formalization of the naturals. That means negative numbers. That means real numbers that aren't integers, well, rather that aren't whole numbers. So never is going to be really useful to us here. So this p of t type makes sense because basically we have the prev pointer on every natural number, and if we go 2 prev pointers deep, we see that we get to the previous number. So that brings us to addition. This looks a little bit scary, but I promise it isn't. So this type add takes 2 type parameters, a and b. These are numbers that we're trying to add. So add a comma b equals a plus b. We can define addition from first principles using the recurrence here that you see on the right. So since 0 is the additive identity, we know that a plus 0 equals a. Additionally, we know that a plus s of b equals s of a plus b. Just by thinking for a minute, we know that a plus quantity b plus 1 equals quantity a plus b plus 1. So that should make intuitive sense. Unfortunately, due to some limitations in the TypeScript system, we can't write the commented out version of this type here because we're not allowed to refer to a type that references itself circularly. So the type that's not commented out here, add, is just an indexing hack to write the type below here. So just walking through this one more time, let's say we're trying to add 1 and 0. If b extends 0, then we index in to the value 0 and we return a. This just means we have b plus 0 equals b. If we have a plus 0 equals a. If we have numbers that are non-zero, all we're basically doing is using a as an accumulator until we get to the base case where b is 0, where a plus b is the same as the successor of a plus b minus 1. Great. Subtraction is marginally more complicated since it doesn't make sense to subtract a larger number from a smaller one over the naturals. So the recurrence needs an extra error term. Otherwise, it's basically the same as addition, just calling predecessor instead of successor as A on A as we decrement B. If B is 0, we have the base case once again, A minus 0 equals A. Otherwise, if B isn't 0, then we have two cases. First, if A is 0, then we have 0 minus some non-zero natural, which is never, because 0 minus some non-zero number is negative, and that doesn't make sense over the natural numbers. So otherwise, we recurse and subtract with A minus 1 and B minus 1 on the operands until either A or B gets to 0. And this makes sense because A minus B is the same as quantity A minus 1 minus quantity B minus 1. So don't worry, I know this is a lot. Once I get through multiplication, I'll share a TypeScript playground that you can experiment with. So multiplication is actually easier than subtraction. It's almost as easy as addition. We can calculate A times B by repeatedly adding A to itself B times. So in the base case, we see that A times 0 is 0. Otherwise, we know that A times S of B equals A times A plus B. Again, intuitively, anything times 0 is 0, and we can basically distribute out the 1 in a multiplication. We know that A times 1 plus B equals A plus AB. So we don't need any error term here because multiplication is closed over the naturals. So assuming we have infinite memory and time, we will be able to multiply any two natural numbers. So a couple little examples. Once again, recorded, we have the original state of our playground, but we've now added these three helper functions, add, subtract, and multiply. They're not really functions, they're types, but for the purposes of this, they are indeed functions. And we see that 6 minus 2, 3 plus 1, and 2 times 2 all equal 4, which is very exciting. And we also see that 6 minus 2 does not indeed equal 5. So a couple sanity checks here. All seem to make sense. The last one, I promise I'm almost done going through the ridiculous constructions, is division. We can calculate A over B by repeatedly subtracting B from A until A reaches 0 and counting the number of times we did it. So that's a little bit confusing. It's the hardest, not least of which because we start running into TypeScript warnings about types that are too large. But its basic recurrence is relatively straightforward. A over 0 is never because dividing by 0 doesn't make sense. Otherwise, 0 over A is 0. Otherwise, S of A over S of B is the same as quantity A minus B over S of B. Basically, the successor of that. We're basically repeatedly subtracting B from A until A reaches 0 and counting the number of times we did that. If we divide by a non-factor, then we'll end up dividing at one point in the recurrence by never, and we'll end up with a never type here, which is exactly what we want because, as I said, it doesn't make sense to divide a natural number by a natural number that doesn't end up in a natural number. So division does warn in the playground because our types are getting arbitrarily big, but we can use a branch of, we can patch TypeScript to make max instantiation depth arbitrarily large to avoid these warnings. Great. So we have addition, multiplication, subtraction, and division. So we can actually finally implement a Collatz type. We discussed a few slides ago what we needed to implement a Collatz checker. We needed division by 2. And since we have generalized division, we have division by 2. We needed multiplication by 3. We have generalized multiplication. We needed repeated application of a function. And I kind of skipped over this, but the TypeScript runtime, or rather the compiler, actually gives this to us for free because we have recursion. And you've seen that we're able to recurse in these types. And so we're definitely going to be able to recurse to the Collatz type. And we also have addition by 1 with the successor type or the generalized addition function. Evenness checking itself is pretty straightforward. If this were an in-person talk, I would ask somebody to describe it to me. But since it's not, I'll get right to it. We can check if n is even by checking if n minus 2 is even. And recursing on that until we reach 0 or 1. So this type just checks if the input is 0 or 1. If it is, it looks up its evenness in a table, since we know that 0 is even and 1 isn't. And otherwise, it calculates the evenness of n minus 2, because we know it's very easy to prove that if n plus 2 is even, then n is even. Finally, with all of that, we can check the Collatz conjecture. If we reach 0, we can say, okay, Collatz checks out. Otherwise, if the input is even, we divide it by 2 and recurse. And if it's odd, we multiply it by 3 and add 1 and recurse, just like I defined the Collatz conjecture. Now, nitpickers may say, but Robbie, this gives us errors when we check whether the Collatz conjecture holds on 3. First of all, 3 is unreasonably large, and I don't know what you're doing with dealing with numbers that big. But second, if you really want, you can recompile TypeScript with a higher max instantiation depth. So our final TypeScript playground with some angry red squiggles will show us magically checking the Collatz conjecture for numbers really up to 3, or bigger ones as long as they're powers of 2. As you can see, these types are getting pretty absurd. But we see that Collatz of 1 is true, Collatz of 2 is true, Collatz of 3 unfortunately is true because TypeScript does assign true to types that it doesn't that are too deep. And we see that 4 and 8, because those are chains of just length 3 or 4 instead of much longer ones like 3, are also true. So I haven't proven it here, but I've hinted very strongly that the type system is Turing complete, and it does happen to be Turing complete given infinite memory. And while the exercise that we just went through is entirely useless in every way, it does teach us that the type system is incredibly powerful, and we can do cool things like write a basically transpiler from a JSON schema to a TypeScript type at compile time instead of at code generation time or something like that. So I'm going to pause here for Q&A, and we can then go through 3 or 4 slides about ts-json-validator if people are interested. But that is what I have to say about checking the Collatz conjecture at compile time.
Okay, thank you very much. It was a great talk, really impressive. Do you have any questions? Let me check the chat. Any questions? Oh, there is a question from Rafael. Could you share your TS playgrounds?
Yes, just a moment. They should be available from that blog post, but I will send the link to that latest playground in a moment. Yeah, the Zoom links are questionable. Thank you, Lillian.
Thank you very much. Do you have any more questions? Yes, someone just linked your blog post.
Right, thank you. Yes, I spoke about a branch for max instantiation depth, which is just to say the way I did it was I forked TypeScript and patched it, but that's all you need to do. It's whether you have your own branch or clone it and patch it, it's the same thing.
Okay, any more questions? Oh, there is a question from Hesperus. You started speaking about a branch for max instantiation depth, but you patched the TypeScript code, right?
Right, sorry, I answered that question without reading it first. The idea is that's exactly right. You make your own branch to increase max instantiation depth.
Okay, cool. Any more questions? Let's wait a second.
Great. In that case, I do have a couple of minutes. I promised a 30-minute talk, so I'll do 5 or 8 minutes about Validator. And so I'm happy to share that. So I imagine everybody can still see my screen.
Yes, yes, we do.
Great. So we can get into ts-json-validator really quickly. So first, we want to chat really quickly about a JSON schema. A JSON schema is just a domain-specific language that defines the form of a JSON blob. And JSON can be validated against a schema at runtime. So on the left here, we see an example of a JSON schema. It defines that we want the schema to have the type object. We have these three properties, A, B, and C, where A is a string, B is a type, B is a number, and C is a string. This title field is basically just a comment, but we see this enum field that restricts the inputs of C to be B1 and B2. And we've also, using metadata here, marked A as required. So this ends up converting this into an equivalent TypeScript type, as A is a string that's required because we have this required field, B is an optional number, and C is an optional string that is either B1 or B2. This is really B1 or B2 or undefined, but this is the same thing as using the question mark here. Great. So what our goal is to generate a TypeScript type and JSON schema pair such that any type that S can validate is assignable to T, and as few types as possible that are assignable to T cannot be validated by S. Now, we need both of these conditions because step one is easily possible by assigning type T to any, but that's not really useful because that defeats the entire purpose of TypeScript. So the idea is we want to narrow the type as far as possible to make this library actually useful, which is where 2 comes in. Now we can't get perfect validation because TypeScript doesn't support some things like regular expression types or certain reference circles, but it's generally possible to make really useful. So we can do a lot here for many keywords, but we can't express every single thing that a JSON schema can express in the type system. So we have a type, JSON value, which basically is a recursive type that allows us to say a JSON value is either a dictionary mapping from property to more JSON values, it's a Boolean value, it's a list of JSON values, it's null, it's number, or a string. And if you look at the JSON spec, you'll see that these are the 5 different things, or the 6 different things that can make a JSON value. And what we've done here is, in order to figure out whether a JSON schema adds constraints, is for every member, for every option in the JSON schema, we add some constraint. For example, we have an enum constraint where the enum is itself a JSON value. What's really cool about JSON schema is it itself is written in JSON. So we know that every single subpart of the JSON value is itself JSON. So JSON.parse could be typed as any, but it's not really useful to do that because it's nicer to type it as this union of these 6 things. So basically the enum constraint says this item must match at least one of the schemas in this enum. So the key insight to making ts-json-validator was twofold. First, we can use previous generics in the definition of future generics. This is something that some people who write TypeScript don't realize. If you have a generic with lots of types, lots of properties, we can actually use, for example, the type variable here in a future property. So this calculated type at the bottom takes all of these constraints that I've defined above, simple type constraint, enum constraint, with these enums that I've defined in the interface, and just takes the intersection between all of those constraints. This means we can use a generic, this calculated type, that nobody's ever supposed to fill in, and make its default value some function of the other generics that are filled in. So this is a bit of a hack, because if somebody does fill in calculated type, then ts-json-validator is going to break. But we have some protections around that, because calculated type is guaranteed to contain some special symbols that nobody else should be able to deal with. So the other insight is that it's possible to annotate each schema with its own type. So any schema can introspect itself at any level. So for this, we used, until we found out that it was broken, a unique symbol. As you can see here, create schema literally does nothing except return the input plus an empty object that is of that schema type. So this adds no overhead at runtime. All it's doing is it's returning the exploded schema plus some extra symbol that is the type of the internal type symbol, which is recursed upon. So finally, we have a little demo, and we see that we've defined this schema 1, which is similar to the one that I showed early on. We see that required prop is required, and now so is enum prop because I just added it to the required array. And we can see that parse2 is of the type that we expect, and that X is also exactly the type of the TypeScript type corresponding to schema 1. And we have convenient autocompletion and convenient error checking and all that good stuff. So if you want to use this in a project, it is currently not quite 1.0, but it doesn't actually do anything at runtime, as I showed, except for add this extra type. So I feel that it's pretty stable. The only thing that you might have to do is if I do make changes before 1.0, you might have to modify some of your type annotations. So that is my second half of my talk. And any questions about ts-json-validator, I'm happy to field as well.